learned life is just a series of random excitations. And all my anxieties, they're just uncertainty relations. Now at last got me a
Here we are with the beady, disapproving eye of Schrodinger's cat angrily staring down at us, ready to disregard that cautionary tale and dive into the mysteries of how the universe works. Let's get started. Two of the most fundamental and pervasive equations that govern the universe are the heat equation and the wave equation. If we study the heat equation, we soon start seeing terms of the form e to the minus x squared and factors of square root of 2 pi start popping up. And yet, at the lowest level, the heat equation can easily be simulated by a bunch of dumb particles, or late-night football hooligans randomly meandering to and fro. What about the wave equation? It's just as pervasive, just as fundamental. Dive into that and you start seeing sine, cosine, Euler's identity. But down at the lowest level, there's nothing but inane platitudes about some mysterious wave-particle duality. Let's put an end to that right now. Can we take those same particles randomly walking back and forth so as to give us the heat equation and make them generate the wave equation instead? Put an end to this nonsense about wave-particle paradoxes once and for all? Stick around. Brownian motion. In other words, particles executing something like stepwise motion so that the direction of every successive step has no relation to the direction of the previous step, is something we see happening all around us. Dust particles floating in air, a drop of ink diffusing into a glass of water, a sugar cube dissolving in hot tea, the way that heat is dissipated or transferred. I'm guessing most of the people who have made it even this far into the video probably know a thing or two about Brownian motion. But let's just briefly run it down to make a smoother transition to what comes next. The simple way to model Brownian motion is as follows. A particle in some space, it can also be a grid or checkerboard or an irregular tiling or even some weird random lattice, travels along in a certain direction and something happens. Maybe a timer goes off, maybe it encounters some other particle or obstacle, or maybe it reaches the next node of that grid. But whenever that happens, the particle randomly picks another direction out of all the ones that might be available to it on this space and starts off again just as before. To make things easier to simulate, let's assume any particles in the space in question follow the same clock and they have the same propagation speed. But eventually even that requirement can be relaxed significantly. If the particle we just considered repeats that random walk over and over, and if we assume all the obstacles and new directions are evenly distributed at some larger magnification, we'll get something that looks like Brownian motion. And if we get enough particles walking together, it turns out that their distribution obeys the heat equation to as close an approximation as we'd like. Now that's a complicated differential equation. Lots of calculus, lots of partial derivatives, doesn't matter. Those dumb and disorganized little particles can make it happen. In fact, their cluelessness about where to go next, to the extent that their choices are completely random and independent of what anything else on that space is doing, is part of what makes it happen. Can we do something similar for the wave equation? Can we find some way to get particles to generate waves instead of just diffusion and dissolution? You might find it doubtful. Waves are about elasticity and momentum and sine waves that go up and down forever, whereas diffusion is just heat death and slack and decay. But waves are fundamental too, right? Especially at the quantum level. So it seems like there ought to be some simple and general purpose way of generating them too, right? The answer is yes, there is. And it's pretty similar to what I just described for Brownian motion, except that the particles will need to have a sign. They can be positive or negative, like a particle and antiparticle, so that particle-antiparticle pairs can pop up here and there. And they can also annihilate. Is that starting to sound vaguely familiar? Well, hold on, we're not nearly there yet. For now, let's just say these particles will be a little smarter than the ones that generate Brownian motion, because they possess a sign, but that's about it. Still very dumb and still very disorganized. And the rules of propagation are very similar to those for Brownian motion. A particle much like the one we just considered except that it has a sign, is moving along in some direction on that same grid or lattice we considered before. When a timer goes off, or when it meets some other particle or obstacle or node or switching station, it randomly picks a new direction for the next step of its journey. But it also creates a particle-antiparticle pair. The member of the pair that has the same sign as the original incoming particle that sparked its creation just picks a random direction. It can be the same as the one that the original particle just picked, and if so, then that's the direction in which both will propagate. But the member of the pair that has the opposite sign must be emitted in the opposite direction that the original incoming particle took. So it not only has the opposite sign that the incoming particle had, it has the opposite direction. Note that the net number of particles is conserved in all this. Of course it was. The creation of a particle-antiparticle pair is not going to increase the net particle count. And that's about it. Those particles will, from that point on, execute the same Brownian motion and trigger a new particle-antiparticle pair, just like the original particle did. But we are going to insist that particles of opposite sign that wind up moving in the same direction and the same location must cancel each other out and annihilate. Makes sense, right? For example, if either of those outgoing Brownian motion particles happen to pick the direction that the backward propagating particle took, then both that Brownian particle and the back propagating particle would annihilate, because they're in the same location with opposite sign. If that should happen, then only one particle survives in that step, not three. But even so, the net number of particles remains unchanged. And if there happen to be other particles there of the opposite sign due to some other particle on our space that happens to wind up there, then they cancel too. We'll discuss what that means for fermion particles later on. It turns out this kind of propagation yields an extra conservation property, as we'll show in a little while. Not just the net number of particles is conserved, but also the sum of the square of the net number of particles throughout the space. And that's an especially useful property given that its expected value is always going to be positive. So even though we had to give our particles a sign, we still have a quantity that in some macroscopic limit will always be positive. But we're not done. It turns out we also wind up conserving momentum on average, because that negative particle traveling in the opposite direction has the same momentum as the original particle, whereas the other two propagating in Brownian motion fashion have zero momentum on average. In fact, we can start with the conservation of momentum and then back out the rest of the collision rules that way. If you want to preserve momentum and you're able to flip sign, there's really only two options available. A particle can keep going in the same direction, which, aside from not being all that interesting, is already assuming too much. And what if we're on some kind of odd lattice configuration, say a hexagonal or a tetrahedral lattice or something even weirder like those diagrams that you see in graph theory? Then we can't always be assured that there is an outgoing collision or branching direction that allows the momentum to be preserved. But that's not the only option available to us. The particle can reverse direction and flip sign. Just go back along the direction it came. And that's a channel or pathway that we already know exists because the particle just used it. And as long as we go back that direction and also flip the sign, we've preserved the momentum. So that second option is arguably the more general purpose one, more so than the more boring choice that assumes a particle traveling in one direction will always be able to keep choosing that particular direction. But if we do go with the second option, we now have a problem in that the net particle count has changed. So if the original particle was positive, implying a contribution to the net particle count of +1, then the outgoing particle after the reversal and sign flip is negative, so that it contributes -1 to the particle count. In order to keep that net count conserved before and after the collision/branching/switching juncture, we need to generate two other positive particles. And it turns out, as we'll show later, they can be in any random direction that the particle has at its disposal, just as with Brownian motion. Someone might say, well, what if we always insist that the two extra particles that are created traverse in opposite directions, because that will make the conservation of momentum even more precise? How about that? Again, that's fine if you're working with Euclidean space, but having an oppositely oriented pair of outgoing directions isn't something we're assured of. And as with Brownian motion, it's not necessary. Because as long as the lattice or grid or graph is homogeneous enough at some magnification length so that those irregularities and asymmetries average out, we'll be fine. That's pretty amazing, right? These particles don't know about calculus. They don't know about Hilbert spaces or eigenvalues or Bell's inequality or anything like that. They might not even have a Euclidean space to walk around in. They're simple little particles just chugging along, doing their little game of life shuffle, colliding, annihilating, creating particle-antiparticle pairs, doing what cellular automata do. And in the end, they create the wave equation, which is what governs ripples that can traverse across entire galaxies. Now you might say, hold on a minute. You just said that Brownian motion appears everywhere. Ink droplets, particles of sand, dust in the wind. Why don't we see this particle wave branching everywhere we go? I have 3 answers for that. 1, the fact that particles and antiparticles have to be created at every step makes the wave process more complicated. Not everything in nature comes equipped with a positive or negative sign. But also, the fact that positive and negative particles are created with every ripple, so to speak, means there's going to be a lot of cancellation. So that there have to be lots and lots and lots of particles to make it work. Finally, maybe the simplest answer to that objection is that we do see it all around us, given that according to quantum mechanics, all matter exists as waves. And I'll show you that moving from the wave equation to equations for massive particles isn't that big of a deal. Yes, we do need to deal with enormous numbers of particles. But it's a good thing that the universe is so vast and full of seemingly empty space that is actually seething with field activity, making it just the kind of venue suitable for these types of waves. So that it makes sense that when we peer at closer and closer distances into the so-called vacuum, that there are all sorts of collisions and annihilations and particle-antiparticle creation there. In other words, we do see this type of wave activity all around us. We're just too macroscopic to be able to directly observe the minutiae of those step-by-step collisions and annihilations. If you want to learn how to prove this Brownian motion plus a particle-antiparticle combo gives us the wave equation, and how these particle waves are useful in quantum mechanics and making sense of the particle-wave dualities that are encountered there, then check out the next couple of videos in this series. If you know about Bell's inequality, don't let that discourage you. Wigner and Feynman came up with a way to get around that is ideally suited for this approach. While we can use it to create a model of quantum behavior where the microphysics are simple and local, that's unfortunately not enough to keep quantum mechanics from being weird and counterintuitive at the Schrödinger cat level, which depends on how all those pluses and minuses cancel out and the path along which the measurements are taken. But our goal here is merely to show how particles and waves can go together. We'll wrap things up by summarizing what you'll learn in the remainder of this series, and this will serve as a handy cheat sheet for what follows for those who want to skip ahead. Following the formalism adopted with Ising models and lattice gases and Brownian motion, we will express the classical wave equation on a lattice as a matrix equation, which, by the way, forces the speed of light to be 1 over the square root of the number of dimensions, that transform incoming flows into a lattice point with n nearest neighbors into outgoing flows. We'll see that the outgoing matrix coefficients for any flow, which are all 1 over n in the case of the heat equation in Brownian motion, are instead all 2 over n, except for the coefficient representing flow in the reverse direction of that incoming flow. And that one is -1 plus 2 over n. The cool thing about those n numbers is that both their sum and the sum of their squares is equal to 1. Tried for n equals 7. Yeah, that works. What about n equals 4? That's good. What about the general case? Checks out too. So to implement a particle interpretation of this matrix equation, we'll assume that every incoming algebraic particle, in other words, a particle can be plus or minus, produces at every lattice point 2 outgoing particles in random directions. That takes care of the 2 over n factor in all the coefficients. And with probability 1, a sign-flipped particle in the opposite direction. We'll see from the matrix coefficients that the net particle count is thereby conserved, which was already obvious, and also the square of the expected net particle count, and also the expected momentum. Note this approach can be extended to any number of dimensions and any regular lattice, even irregular or random lattices, as long as the expected vector sum of the directions of the lattice nearest neighbors, when projected onto Euclidean space, is 0. In other words, as long as Brownian motion on the lattice is a good representation of the heat equation. For sufficiently sparse and uniform deformations in our lattice, the wave equation becomes, by way of a first-order perturbation, the Klein-Gordon equation. So all this works for wave functions of particles possessing mass. Finally, we'll again relate this formalism to quantum mechanics using earlier work by Wigner, Feynman, and Dirac regarding generalized probability, or in this case, the probability of net particle counts, and the simultaneous product of 2 independent net particle counts, which happens to be a positive number for any sufficiently macroscopic accrual. That'll be it for now. Thank you for watching. There are a lot of cool science videos out there whose creators could use your help and support. This one's on me, but if you liked it, please click on the like button and feel free to go give something to one of those other content providers. And if you know anyone who is interested in how quantum mechanics works, or in graph theory, or cellular automata, or propagation on the lattice, please share this video with me.
I can't begin to tell you all the magical things I've seen. To the secrets of creation, I was given on a platter the key. And finally I figured out what was the matter with